Okay, folks, the ranks have thinned here. But look, what I wanted to do first was just go over a little bit of what we did yesterday, just to make sure that we didn't leave things hanging. And then I wanted to tell you, give you a brief outline of where we're headed today. So yesterday was all capillary, no elasto, right? We started by talking about defining the surface energy through the work done needed to create new surface for any condensed phase, but we've really been thinking about liquids. Okay, this quantity, it has units of energy per area, and we found that you can get reasonably sensible estimates of what this object should be by taking what it takes to make the condensed phase, the cohesion energy to make the condensed phase divided by some typical molecular area squared. And this gives a reasonable first pass at what you might get for the value of this object. We spoke a little bit about this, then we recognized, of course, that this also has the same units as force per line. And we talked about some situations in which you can mimic what you get with surface energy considerations with things that look like forces, okay? Forces per lines. Okay, then we talked a little bit about what it means, what are the implications of area minimization. If you want to minimize area and you have no other constraints except that, for example, you're held against some boundary, then what you get is that you get a surface whose normals are divergenceless. And we argued that that's the same thing as having zero mean curvature. This object was the mean curvature. If you have some other things going on, some other constraints, and you often do, the most typical of these being a volume constraint, then you'll get shapes that do have mean curvature. It will not be zero. And the most common thing you can think of is a drop. Okay, this is an object that's nearly spherical and it has mean curvature. And if you add these other constraints, you get shapes that don't fall in this zero mean curvature category. What they come with is a pressure. There's a pressure jump across such an interface. And that pressure jump is given by twice the mean curvature. This is actually just the sum of the two curvatures, okay, times the relevant surface energy. That's equal to a pressure jump, which you recognize to be the Laplace pressure inside drops or bubbles, but not just inside drops, okay? This is the pressure that you feel at any place where the surface undulates, has with mean curvature, okay? All right. We saw that this can be for small enough drops large, okay? That pressure has the units of a stress or a modulus, and that value can be easily the modulus of something soft, okay? Then we brought into the picture a solid, and we started talking about gravity for the first time. In thinking about drops here and drops making spheres, we just said, for the moment, let's say we know what, for small enough drops, gravity doesn't matter. We brought back gravity explicitly when we looked at one of these problems. This was a capillary rise problem. We did the version between plates. So this thing looks like that, okay? And there's a fluid that rises in between them. from a reservoir of fluid. We figured out, again, just from now two things. We have gravitational potential energy, and we have the surface energies of the solid, the liquid, and the vapor above to take care of. Just with those considerations, we figured out that the capillary rise goes as the difference between the solid vapor and the solid liquid surface energies divided by rho g, and it changes, of course, with a gap. This thing better be positive. That's what's driving the whole process. This pink object, the solid, would prefer to be wet by the liquid than it would prefer to be wet by air. Okay. Importantly, there's no gamma liquid vapor in here. It's not a player. In passing, we noted that this guy must have the dimensions of length square. You can check, because length square divided by d has to give a length. Okay? That same combination of symbols showed up shortly after, when we started looking in detail at this shape over here. That shape of the meniscus we figured out using the considerations we'd already thought about here. Area minimization with gravity now. You put gravity times the curvature equals the pressure jump. And you can put in the equations we did for curvature. In the linear case with small slopes, this thing is just an exponential. But the scale that governs that exponential is now gamma LV over rho g. Okay. So that's this thing, this scale over here is LC. And this is called the capillary length. Okay. This is millimeters for most of the things you handle in the lab. For water, air, it's a few millimeters. It's 3 millimeters. Right? Okay. So now we know what to call small. Small is objects. Small in the sense of you're allowed to neglect gravity, or objects at the scale below LC. Okay. Then we started thinking about two cases of three-phase contact. The first one was a drop placed on a rigid substrate, rigid solid substrate. And we got sort of what's called the classic Young-Laplace-Dupre contact. Okay. How do you get to go first when you're alphabetically last? But we worked this out from energy minimization. And we found that this contact angle, which is the only thing you need to know, given the volume, to specify this shape, is given by this combination of the relevant surface energies. This is the same guy, gamma SV minus gamma SL divided by gamma LV. Again, for small drops, which we now know is drop volume less than LC cubed, this is a spherical cap. Right? I think there's some things we said about this that are important to carry forward for today. The first thing is that if you transpose this here, gamma LV cos theta, then you can start putting arrows here and interpreting this as some kind of horizontal force balance. Okay. For what that's worth, you can add any further stress in this plane. You can add another arrow corresponding to some stress on the solid, and it'll make no effect on that horizontal force balance. So this is unaffected by free stress on the solid. Okay. That's one thing I wanted to say again. The second thing I wanted to say is, how come we didn't get any kind of equivalent of vertical force balance? That we said, sort of the underlying story was, we put that in as a constraint. We said this bottom surface is going to be flat, okay? We're not going to allow the contact line to move up. And what the interpretation there is, you know, maybe this contact line wants to ride up, but this thing is able to provide any kind of restoring force that's needed with unnoticeable strain. Okay, that's what we looked at in that case. Then we looked at the liquid drop on a liquid bath immiscible objects situation. Again, we looked at the shape just by minimization. Again, small drops. And here we had to figure out two things. We need to figure out one angle here and another angle, one angle above the horizon and another angle below the horizon. Okay. And here we got two conditions that were we didn't work through that in as much detail, but we got two conditions that are the equivalent of horizontal and vertical force balance. Here, the question of adding stresses in plane doesn't arise. There is no way to modify stresses over here. You can't just pre-stress this thing. There is one unique value that the stress wants to take, and that's the value of the surface tension. Okay? But what you do get is something like vertical force balance. Okay, so where we are headed today is very soon adding our first elastocapillary interaction. And let me just give you a slight roadmap of what's happening today. Maybe I should first ask, are there things you wanted to talk about there? We're okay? All right. So I'm going to, based on your feedback, mainly skip telling you what elasticity is and move on from there. I'm going to show you a first elastocapillary effect, which looks a lot like the Young-Laplace-Dupré experiment, except we'll take that red object, the solid will now be of finite elasticity. And we'll see how that changes the picture. Okay? And you'll see that there's one new length scale that will show up there. And that length scale is going to give you a sense of whether this is important or not important. Okay? And we'll discuss it through an example. We'll discuss it through, I think, both a useful example to think about because it connects with the kind of simpler pictures we have, but also practically important example. Then we'll see that effect mainly comes from the fact that the substrate is soft. We'll find that as you make the substrate less and less rigid, this effect becomes more and more pronounced. I'll then turn the conversation to making elastocapillary effects with things that aren't made of soft materials, but that are thin, so that they can deform easily, even if they are not extremely soft objects. So we'll spend a few minutes talking about just introducing elasticity of thin objects. Okay? And then we'll move on to an elastocapillary effect in a thin sheet. We'll talk about how you reduce elasticity for a rod and a thin sheet. Okay? And then we'll talk a little bit about, again, an example that I think connects with one of the things we have done and is therefore useful to think about, but is also, I think, practically important example. Okay? And you'll see that we get length scale number 2 today. That tells another kind of important elastocapillary coupling. Then we'll try and do some more things with that, okay? So really the menu here is, I would like to complete this picture. I'm going to stop sharing because I think Can I stop sharing this? Okay. So schematically, I'm going to add to this with something soft and have a drop come on it. Then that's the first set of things I'm going to talk about. The second set of things I'm going to talk about is something like making this flexible. Make walls flexible. Okay, that's the plan. Before I launch in, there's one thing I thought as I was listening to all your talks yesterday, all the 1, 2, 3 minute talks yesterday. And that was that we've been dealing a lot with the simplest possible cases, whereas all of you work on fairly complicated situations where there's particles, molecules, all kinds of things at surfaces. Okay, so I just want to say a word or two about where, I won't know about your specific experimental situation. I'm happy to chat about with you privately, but I just wanted to tell you a little bit of where I think these things fit. Okay. See, here's a static bulk solid. Okay. The compression modulus is finite. The shear modulus is finite. And the state of stress can be really complicated. Like I can have all kinds of forces on it. You can have shear stresses, volume stresses, all kinds. And really, you have to do force balance to pull out all the stresses. In a static bulk liquid, the compression modulus is finite. The shear modulus is 0. Pretty much defines a liquid. And the state of stress inside is very simple. It's pressure, it's isotropic. Okay? This thing is an isotropic object. Now, we've spent most of our time and will spend most of our time talking about this kind of liquid, right? The interface of a bulk liquid. Here, the compression modulus is 0. We saw that yesterday. If you allow it to, it'll just want to run down to as small a volume as it can, okay, by itself. You don't need to help. The shear modulus is 0. This is still liquid surface. The state of stress is given by some surface tension that's isotropic. You can't do anything about it. Okay, it's the same surface tension in all directions, and it's A value. It's A value because even as you change the shape of the liquid, there's other liquid molecules in the bulk that can enter and just replenish that surface. Now, if you put stuff at the surface, okay, if there's an unlimited supply of this stuff in the bulk, then everything that we said here will be true. You have created an experimental knob to change this value. Fine. Okay. But everything else that we said here will carry over. If you have some interface which you have decorated with, I don't know, particles or surfactant or something like that, and this is in limited supply. Say it's only available at the surface. Okay? And say the value of the surface tension depends on the coverage of these particles. Then everything's okay, except that as you change the surface area, this number will change. Okay? Right? Now, if you start making the surface more and more crowded, so that each of these particles start seeing each other, then the new thing you'll develop is that you'll have the ability to sustain some kind of compression. Okay, these things can see each other, interact, push each other apart. You won't be able to, may not be able to go to 0 volume. And for the same reason, you can create states of tension in this, people who work in these kinds of systems know that tension is a variable. Okay, it's not just a fixed number. All right. And then if you have your surface so crowded, or if you actually have an actual solid at the surface, then you have a finite shear modulus as well, and you can sustain weird anisotropic stresses like a solid. Okay, so I've mainly been talking about this stuff, but you should recognize that everything we're talking about probably carries easily over into this. Start worrying and thinking afresh if you live here, and this is different. Okay, if you actually have a solid at the interface, we'll talk about that today. We'll talk about putting a thin solid at the interface. Okay, so we'll explicitly talk differently about this. All right. Okay, so we're going to start now thinking about this object, and really you can begin to anticipate what you might get, right? We're going to get something that looks like this. It's going to make some, let's say it makes some deformation on the surface. It's clear that the free surface, we're still at V0 much less than LC cubed, okay? Is it okay for you that the free surface is still spherical cap? We're good with this? Nothing's changed about that interface, right? What we have to do is figure out this stuff. All right. So what do we have at hand to figure out that stuff? Let's think basically about solids that are isotropic, homogeneous, Hookean solids. Okay, as you know, these are the elastic properties can be specified in terms of two numbers. You have a Young's modulus and you have a Poisson ratio. Yeah. This number can span a huge range of values. Okay. Did I bring a slide? I think I brought a slide. I like this slide if I have it. Can you read the things over there? Okay, so this is Young's modulus going from 10 to the 11, 10 to the 12. The blue things are synthetic engineering materials. There's steel and there's the kinds of things you may use to construct your equipment from. There's glass, there's nylon, there's plastics, rubbers, et cetera, down to silicone elastomers, hydrogels. You can go much, actually you can go lower without much well, you can get gels that are well below that 10 kilopascals over there, but it's a huge range, right? The green things are you and me. It's all stuff in our bodies, and shockingly, you can match almost the whole range. Okay, so this number that we have is just all over the map. Unlike the gammas that we were dealing with, right? The gammas we were dealing with typically that we had available to us was a small range, not 9 orders of magnitude. All right. So this thing has huge range, and this is this guy runs from -1 to half. Right? The negative numbers are unusual, and I'm not even going to think about them so much. The negative numbers are things that get thinner when you squash them, right? these are not things, there exist those materials and the possibility is there, and you can get engineered materials that look like that. But really, all of our life is somewhere in the 1/4 to 1/2 range. Most of the things you deal with. And in fact, many soft things are really quite close to 1/2. Okay, so I don't know what kind of things you deal with, but many rubbers are actually close to 1/2. And 1/2 you should realize is incompressible. 1/2 means if you squash something 1 unit this way, it expands 1/2 a unit in both directions, so you retain volume. Okay, so many rubbers are close to 1/2. Many elastomers, for example, the standard formulation of PDMS you use, you know this stuff? It's an elastomer. This is close to 1/2. Okay, it's nearly incompressible. So if, you know, those live near 0.45, 0.49, etc. Okay, so many things that are interestingly soft will live up against this wall. All right. Okay. Of course, the other way of writing all of this stuff is instead of these two parameters, you can write things in terms of a bulk and a shear modulus. And these are, of course, equivalent sets of numbers. It's worth writing out that equivalence for a second to realize a little bit the significance of what we just said about numbers here. Okay, so in terms of the Young's model, okay, so this is in terms of this, the bulk modulus is and the shear, oh, I was told not to write so close to the top, is E over 1 plus lambda. Okay. You can see what interesting things happen when you push up against incompressible. Okay. So the scale for both of these is set by the same Young's modulus. Okay, but their ratio is, you know, controlled a lot by the Poisson ratio. Right? So you know, if I look at, for example, E shear divided by E bulk, this is okay. Right? So of course, E shear is always non-zero. But as you can see that as you go up against the incompressible limit, it becomes much, much easier to shear than to change volume. So if you give it the option, if you give us, okay, let's say this, so here's let's say elastic energy density. Okay, this is something like half E bulk times volume strain squared. Okay, plus half E shear times shear strain squared. You might think that, you know, this is the larger number. This is where you'll pay the energy. That's not what's going to happen. Unless you force the material by boundary conditions or geometry or constraint to change volume, if you give some relatively unconstrained boundary condition and push, it's actually going to put all its energy into this, and it's not going to change volume at all. It'll avoid touching this piece, And basically, it's the shear that's going to take almost all the action. Okay. All right. So with those comments, I just wanted to head back to our case here. And let's think about what might happen to this object. We have everything we need over there. So let's ask now how soft we need to be to make anything happen over here. Okay. So I'm thinking about this guy, okay? So the scale of deformation is some kind of surface stress divided by a modulus. Okay. So this is some energy per area. And this is some energy per volume. Okay. And you know what these energies are going to be. This is going to be, in this case, the gamma. And here, I've tried to argue strenuously that unless there's something specific going on, it's going to be yes. Okay. It's going to be sort of the shear component. Okay. So this quantity, this is called the elastocapillary length. Elastocapillary length. LEC is just gamma, and I'm going to just say here. Okay. So let me give you a sense of, I'm going to start erasing here because I don't need this stuff anymore. I'll leave the other cartoons up for a moment. Okay. So let me just put in a few material numbers and then you'll see. So this is, I'm going to put in Young's modulus and I'm going to say, so let me pick a garden variety polymer. So this is glassy polystyrene. This is something like 3 gigapascals. LEC, sorry. Again, I think I'm moving a little far up the wall for visibility. E, this is polystyrene. This is 3 gigapascal. LEC is with water air in, is so this is 72 millinewton per meter divided by 3 GPa. Okay, this is 0.24 nanometer. Okay, so for a material like a normal plastic, it's, forget it. All right, it's, even this number is so tiny. Okay, so if you're thinking of a microscope slide and a drop of water on it, you can tell this doesn't matter at all. All right. But for something like this, it's okay. Okay, so now let's go a little bit. Let's do a made-up elastomer who is exactly 100 kilopascals. You will get LEC of 0.72 micrometer. Okay, which is okay. Now I can see this, but it's tiny. And if you do say a soft gel, say a kilopascal, this is the kind of thing that starts falling apart under its own weight if you make enough of it. But it's fine. This becomes a big object. Okay? So what you see, so you can actually solve this elastic problem in detail, but the cartoon version of what this looks like is this thing gets pinched upwards. Remember, we had to account for that gamma LV sine theta. This is what happens over here. With it rises up to meet the thing. And now there's also, remember, there's a pressure inside this drop. So there's a Laplace pressure pushing down on this material. So this guy does that, but it also gets deformed slightly underneath the surface as well. Okay, this scale, this is LEC. And if this thing is actually very, very deep, so is this scale. This scale of deformation. So there's just that one scale. Now, this is what it looks like when LEC is still much smaller than the size of the drop. Okay, so the elastic problem you solve is I place an upward force acting up on an infinite half plane of this stuff, pulling upwards. Okay, and you can solve that correctly with the Laplace pressure pushing down at the bottom, and that's what this looks like. So people had thought about this a while ago in the 80s. And I think Shanahan was the first person to think about this and really advocate for the importance of this kind of thing. I forgot to say, this object is called the wetting ridge. That object, this object, called the wetting ridge. All right. Yeah, so here's the wetting ridge visualized in two different substrates. Here's actually, these are very detailed visualizations made by Park in 2014, both by X-ray techniques. And there's no mystery. It's perfectly understandable elastic calculation. It works extremely well. One thing that was realized very early on by Shanahan himself and co-workers was that this thing, even if it's small, it can have a big effect on the motion of drops, dynamics of drops even if it looks like it's made no difference to the structure, like you have a millimeter drop and you have a sub-micron little thing over there, they pointed out that it can still make a big difference to motion. So what happens, so say you put a drop on, well, not on that surface of this, but say you put a drop over here and you let it slide. The main dissipation you're going to get is from the viscous dissipation of the drop. Okay. Here now, I can't even do this, right? It's a curved ridge. But every time I move the drop, this curved ridge has to move a lot, has to move with it. Okay. So there's a lot of dissipation in the solid itself. Even if it's a tiny object, you're actually rolling out the solid in front of you and behind you. Okay, so it can impede droplet motion a lot. And I show you examples of this. Here's an example of what they call viscoelastic braking. It's viscoelastic braking not because the drop is viscoelastic. The substrate has a huge viscous component to it. And this is simple experiment. You put a drop of, you're just actually watching a drop spreading on a surface. Same thing, right? You make a ridge, and then the ridge has to expand further and further out in ripples till it reaches its asymptotic size. And that's a process that really slows down. It's a logarithmically slow process. The stuff RTV 615 is an epoxy. It is, I think, did he say? Not here. I'll add this to the slide, but I think it's about 1.5 megapascals. So quite stiff stuff. Okay. Here's another pretty one. This is from the group of Eric Dufresne and Rob Style. This is using the fact that there's a wetting ridge. If you have a gradient of softness, then one side of the ridge is different from the other. The ridge on one side is different from the ridge on the other side. And the droplet may feel advantageous to move to certain places. And so the experiment here is they just spray a surface with a mist of glycerol drops in this case, so that they don't evaporate. And chemically the surface is completely uniform. And you see what the drops end up doing. They try to go to specific places on this thing. The places they go to are designable because they've basically chosen the substrate stiffness in a periodic way. Here, the way they tune the substrate stiffness is by an effect I haven't talked about, actually. Everything I talked about there assumes an infinite substrate, infinitely deep thing, where the only thing that matters then is the elastic moduli of the substrate. If there's a wall underneath, then the depth of this layer also becomes an important variable. And in this case, that's what they've chosen to modulate. So they have the same film, but then they have a corrugated surface underneath. And you can make the drops migrate to where you choose. So they've borrowed this. I saw the word durotaxis in one of your things yesterday. Yes, please. You were the one who was talking about durotaxis. Thank you for reminding me. What is it was cell crawling. So that's where the word is borrowed from. It came there before. It came in that field, migration of cells along rigidity gradients, and that's where they borrowed the phrase from. Okay. Here is a related thing that I won't talk about. This is sort of a wetting of a solid on a solid. That's a solid drop acting on, you get a similar looking ridge. Won't talk much about that. Here is, I think, maybe morally similar, but not exactly the same as a wetting ridge. This is splashing, okay? So this is splash on a rigid substrate, which itself is a whole interesting problem. Perhaps some of you in the room have worked on it. This is on a slightly compliant surface. And you can see there's much less satellite drops. And this guy is, modestly more, but it just kills. So again, there's a huge amount of dissipation in the substrate. This thing is not the static wetting ridge that I've talked about. Okay. Anything else you'd like to chat about at this point? Okay, so that's our first elastocapillary effect. Excuse me. And what I wanted to say is that we have now built a little vocabulary of these things. I've drawn them in different sizes and different shapes, but these are the two classic cases. Here's another case. Here's where elasto and capillary interact in an interesting way. What I wanted to start thinking about a little bit now was things that aren't tuned by material softness. But for example, I wanted to start thinking of a case that looked like this. Here's a liquid surface. And I will come in with a liquid drop. But what's going to, well, I don't even need the liquid surface, but I'm going to come in with a liquid drop on a solid, but with no specification of modulus, but a thin solid. And I'm going to try and ask what happens here. Now you might ask, how is this solid being held up? One of the simplest ways to hold it up is just by tension, clamping the edges. Another way to do it is by having this thing floating on fluid. Okay. This object can be made of anything. If it's thin enough, it's going to respond differently than this case, and it's going to respond differently than this case. All right. So I want to try build up a little bit the vocabulary for how you deal with situations like this. That's what I'm going to do. Now, it turns out that this one, the problem that is the exact equivalent of this sort of this thing 2D is a tricky one to deal with. And we'll come back to it end of day 3. Okay, that's where I want to head. But I want to speak of this things that are in the spirit, but that are 2-dimensional. Okay, that's why I want to take something that's like your what's it called, the capillary rise experiment along parallel flat walls, something like that, which is a more 2-dimensional thing. Deal with that first, build up that language, and then we will come back Monday and talk about situations that are really look like this and things where we want to wrap a droplet inside a sheet like this. Okay, so for this, we need to talk a little bit about thin sheet elasticity, thin sheet, thin filament elasticity. Yeah. We'll get to that. It's the same answers as to, so I'll give you a detailed answer, but it's going to be the same spirit of answer as we had over here, right? How soft does this have to be? It has to be soft enough so that important length scales in the problem are beyond some threshold. So we're going to construct length scales. So you could have asked, what does this need to be? This needs to be enough so that it starts playing a role in the macroscopic dynamics of this thing, right? So more than that, if you hold on for 15, 20 minutes, you'll have a more detailed answer. So just to repeat the question, if I'm getting it right, can this influence droplet shape, this kind of effect? Often we think of droplet shape when you get irregular droplet shapes as coming from chemical inhomogeneity, for example, on the surface. Could it be, for example, mechanical inhomogeneity, softness gradients on the surface? And the answer is absolutely yes. Yeah, you can, one direction can be much, much slower to get to equilibrium, one part of than the other, for example. A hanging drop. So ask your, a hanging drop, where do you want to put the solid in the hanging drop? Maybe I can show you a hanging drop problem tomorrow, and then I'll start tomorrow probably with a hanging drop problem, and then let's maybe that'll give a context for the question. Yeah. Yes. So the question is, does this help us understand contact angle hysteresis? I'd say that is a whole additional um, layer of interesting stuff. So I think you heard in the previous question something in that vein, right? Can you control sort of dynamics in some way using these? And I think the answer is yes. If we didn't have any elastocapillary effects, would contact angle hysteresis go away? The answer is, I think, pretty clearly no. So I think these are both effects that live in this in this sort of arena of materials that we deal with here. And it's, I think, a different knob now to try. Okay. So if there are, okay, I'm going to now go on and tell a little bit about thin sheets now. Okay, so what I will say will apply mainly, it will apply equally to thin sheets and thin rods. All my examples will be for thin sheets later on, partly because that's what we work on, and partly because there's at least one interesting simplification. But the idea here is there's going to be a few basic modes of deformation of a sheet or a rod, right? If I take something like this, and I try to manipulate it with forces, the state of strain can be, very complicated. And there's very little I can do to reduce the geometry a lot. However, if I start looking at, I don't know, a thinner object like this, okay? I could try doing that. I don't want to do that too enthusiastically, but I can, you can see that there's going to be simpler and simpler descriptions available to you once you realize that if you go even thinner, this thing really can do this, or you can pull, okay? So you can decompose all kinds of response to essentially stretching in plane, things that produce in plane strain that change the length of an object inside the material, or that look like this. So we're trying to do a description here that involves some kind of simplification where we don't need to worry about what's happening in the thickness of this material. That's to say, I don't really want to know, I don't know, gradient in stress as a function of thickness of this. I just want to know the overall shape of this object. So here's the way I will deal with it, or the way it's dealt with. I'm going to write something. Yeah. So I'm going to make a deformation of this object that involves only pulling this way. Or I'm going to make deformations of this object that involve going that way. All right. In either case, so you could think of this as, sorry, you could think of you could think of this as standing for this, or you could, that's a horrible slab, or you could think of this as a section of this object, okay? What I've drawn over there. So you please keep filament or sheet in your mind, whichever you prefer. I'll be drawing sheets. Okay, but if you can make the substitution for filaments in your mind. The idea here is that I don't want to keep track of what's going on as a function of this height. I really want to think of the geometry just of some imaginary plane that runs through this object. Okay? And I want to keep track of just that. So whenever I want to talk about stresses or changes in shape, I really want to think of that dotted line. Every other quantity, I actually want to integrate over the height. I don't want to report for you strain as a function of height over here. I want to take that out of the problem. All right. So, very schematically, like the thing I just erased for bulk elasticity, where we did E bulk times volume strain squared plus E shear plus shear strain times squared. What I would like to write this as is I'd like to be able to say the energy density. So that is elastic energy per area of a sheet. If you're thinking filament, elastic energy per length. Okay. I want to be able to break it up into something that goes as in plane strain. That's to say stretching squared. And this will have some coefficient. Plus in plane bending, plus bending. So the bending, there's nothing that depends on slope of this. The first thing that enters is curvature. It takes energy to curve this thing, and it doesn't matter which way I curve it, whether I curve it this way or that way. So this is going to be some curvature squared. Okay. Now, just dimensionally, you can see that these two material properties, Y and B, are going to have different physical dimensions enter. Okay. Right? Why is that? You can see here you can see that this is a dimensionless. I've lost track of. Whereas this is 1 over length squared, right? Curvature is 1 over radius of curvature squared. So these two have different dimensions. This guy is called the, okay, I must not write there. The stretching modulus has dimensions of, this is energy per area, that's nothing, so this is energy per area. We need to cook up something that has energy per area units, okay? And the bending modulus B is what? Energy per area, and this is 1 over L squared. So this is just units of energy. Okay. So what do you have available to me? What do you think goes into this object, into creating the bending rigidity and the stretching rigidity of this object? What do you think what are the variables you think we have at hand to be able to cook up these quantities with? Any thoughts? So what would I need to do to change, to get a sheet of a certain rigidity? What variables can I control? If I want something that doesn't bend or bends or... So the thing I want to say is, even this object, this is a continuum object. In the third dimension, this is tens of micrometers thick, okay? So everything you have about bulk elasticity when you zoom in enough, works fine. Okay, so you just have the quantities you had in bulk. You can change the Young's modulus or you can change the Poisson ratio. The only other new thing you can change is the thickness. So these are the only things you have at hand. You've got to work with, these are the things. These must be made up of Young's modulus, Poisson ratio. Not much help because it's dimensionless. It may play a role, but it's not going to give you. But now there's the thickness of this object. And clearly, thickness matters, right? A thin piece of rubber stretches more easily than a thick piece of rubber, right? So thickness must enter somewhere here. Okay, so just dimensionally for a sheet, okay. So dimensions of this object are that's energy per volume. Young's modulus is force per area, energy per volume. Yeah. You multiply by thickness, you get this. So this should go. Okay, so this is energy per volume. You need one dimension to get right. And that's the thickness I put in. Here, this thing scales as Young's modulus. Then I need to get rid of a volume, and it's thickness cubed. Okay. The answer for rods, it's energy, it's elastic energy per line. And I need to actually integrate not over just this thickness. I need to integrate this way and that way. And I need just something per line. So for rods, the answers will be ET squared and ET to the fourth. Okay. So these things have very, very strong dependence on thickness. You double thickness, you get a factor of 8 in bending rigidity. Okay. So I'll put in notes a little bit where this comes from. Okay, a proper calculation of how you integrate across the thickness, and you get these values. But I think I want to say some things just schematically. Here, when you're pulling at this piece of material, you're taking absolutely every single thing in here and subjecting it to tensile stresses. Okay, every piece of material is being pulled on, in this case, actually by the same force. It's continuous through this medium, right? In the bending situation, it's a little bit different. When you do this, this piece is under tension, right? This piece is under compression. So there's a piece in between, somewhere here, where there's zero compression or tension. Okay, it's a neutral state of stress, and it, as a result, you know, this maybe is some intuition as to why this is easier than this. There's some piece of the material is not having to do very much at all. Okay. So once again, I want to go through a little bit of an example to say how much easier this is than that. But then we can go on to discuss another Elastocapillary effect. You know, we have sort of the language together, but I do want to show you that, you know, this is really the easy mode of deformation, just as your intuition says it is. So, any questions? Okay, we move on. Okay. I was trying to avoid, no, I won't. We've already thought about LEC. Okay, so the simplest place to put this to use and develop an intuition that bending is by far the preferred thing if things are small enough is this classic situation of buckling. So I take this thing, and I'm now not going to draw the whole piece of material. Okay, I'm just going to draw that center line, and this has got some size W. I'll keep drawing solids in red. And now I'm going to say, I'm going to apply a force. No, I'm going to push this and cause it to move by some distance delta, okay, this edge. This guy can respond in one of two different ways, one of two extreme ways. One is just to shorten distance. This is pure compression. The other is to not change its length at all and just bend, okay? It can also do anything in between. It can do a little bit of this and a little bit of that. Okay, it can change its length modestly and still curve. Okay, but this is the pure stretch piece, and this is the pure bend piece. And just to give you a quick sense of the, so in general, the energy, let's say this object has some extent here. Okay, so I'm just, you can imagine something that looks like that. And this is the width. Then the energy per width goes as the half y times just the strain now, strain squared plus half b times curvature squared, okay? In general, but for just the pure stretch, what it does is just for stretching, use stretching. If it accomplishes everything by stretching, it's half y. And the strain now is how much I asked it to move, you know. Okay, that's how much energy it takes. If I just do U bend all by itself, it's half B. And then there is a little bit of geometry here in figuring out what the curvature is given all of these dimensions. But let me give you that answer. It goes as half B. I'll put in the notes the little bit of geometry that gets you this. So you can see if I plot as a function of delta what these cost, then U stretching is harmonic. Okay, this is U stretch. Okay, it goes as delta squared, like a good Hookean spring should. This guy starts off expensive. It's linear. But after a while, it wins. It's the cheaper thing to do. Okay? And this is sort of the classic buckling problem. You push, you push, you push. Nothing, everything is absorbed by in-plane stretching. Then suddenly it does this. Okay? Once you're beyond that place where it suddenly does this, it becomes incredibly advantageous to do just bending. Don't share anything with stretching. Okay? So The place where this happens is where these two become comparable is when, y, let's say it's at some value of delta that we'll call delta critical. We're going to call this delta critical. When y times delta critical over w squared becomes equal to b times delta critical over w cubed. This value, if I ask now what delta C is over W, this goes as B over Y times 1 over W squared. Now, B goes as Young's modulus times T cubed. Y goes as Young's modulus times T. And then there's a 1 over W squared. Okay. So this, you realize, is just T squared over W squared, independent of any kind of material parameter. Actually, not quite true. There's a Young's modulus, there's a Poisson ratio somewhere in here. Okay. I didn't put in the detail of the Poisson ratio dependence. Okay. But the idea is that you could make this out of steel or you could make this out of paper. It's going to go at the same value of displacement. All right. And once it goes, it will really want to go into the bending. Okay? This number, this W squared over T squared is called the von Karman. Again, it's got, I'm missing there's, it's called the von Karman number. I'm missing things that have to do with Poisson ratio here. But nothing dramatic, okay? All right, so when material thickness looks like this, when material thickness is really small, what's going to happen is you can think of this as completely, instead of writing something like this, you should write something as purely bending plus a constraint that length will not change. Okay? So it's in the same spirit as we did a few other things before. Once something becomes expensive, just don't do it. Okay? So now there's a huge family of shapes that you can achieve using schematically just this. U is bending energy plus constraint. And the constraint is no length change. Okay, instead of bending energy plus stretching energy. And these objects are called Euler elastica. So there's a large vocabulary of these shapes. This is problem posed well before Euler, this kind of shape. Suppose you have an object, you have a fixed length, it won't stretch or compress. What shape does it take? And Euler has solved this for, every kind of boundary condition. And you want to do this, you want to hold this fixed, you want to hold this clamped, you want this joint to be free. There's a large vocabulary of these shapes for you to take advantage of. Okay, so we're going to take advantage of this in our next elastocapillary phenomenon. And that's this. What I'm going to try and do is think about this shape. Okay, so here's sorry, I didn't take a whole sheet, but just a small ribbon. This is morally a sheet. Okay, if I hold this together, what I get is this is an Euler elastica shape. But we're going to try and see what happens when you wet the object. And actually, this is a shape that if you have long hair and the right kind of hair, that shape that you're probably very familiar with. Sorry, I'm just wetting this object. You get a shape that looks like so. Okay? You've seen hair and string and things like produce this kind of shape. Okay, so this zips up a bit. All right. You can do it this not with just with a I've just put wet pieces of string here also. Oops, sorry, make a mess. String is a little bit more complicated, like your hair, but in principle, it has the same kind of shape, which I don't know if you can see. Okay. Should I? Oh, I'm sorry. I should have maybe. No contrast, right? Background is just too bright, right? But do you know what I'm? Do you know what I'm showing you? Okay. Yeah. Okay. It's a familiar shape, right? So that's a very. This is purely elastocapillary in origin, and I want to maybe. Yeah, here's another piece of thread, etc., etc. But the idea is that this is a wet piece of. Oh, here's a bigger one. Okay, maybe this is. Yeah. Maybe that's better. Okay, for our audiences at home. All right. So I want to discuss this very briefly as maybe the last thing we get to do today. Yeah. So here's what's going on. You have all the pieces of information you need to understand this so-called elastocapillary racket, right? You get that classic tennis racket shape. And let's think about where it comes from. Feel my laces get away from me. So we're starting off. I'm now going to actually draw the thickness of the material, even though we're going to go back to our old formulation. I'm going to draw the thickness of the material, and I'm going to draw it wet, okay? So there's a water layer around it, okay? And this thing starts off with some length L0. Yeah. Crudely, where it ends up at is something that looks like this. That's terrible. Something like a circle. This guy goes like this. All right. And now it's wet here, and it's wet here, and it's wet here, and it's wet here, and it's wet on the inside as well, and on the inside of this as well. Okay. So what's driving this to happen? What's driving this to happen is that initially you have the energy density is, no, the energy is just basically gamma LV, this is purely surface energy, times L0 per width, okay? There's a width going in here, which I'm not going to draw, all right? Maybe I should draw two gamma LV, importantly, actually. The top surface is wet and the bottom surface is wet. Good with this? Okay. What we are gaining here is that some of this piece has folded back onto this, and you've taken away some piece of the interface. Okay, so you gain some gamma LV. All right? What you pay is that you've had to twist this piece into a circle. Okay? So the new situation is there's no U elastic. Okay. Here you have the outside thing is still decorated. It's a gamma LV times L0 plus just this stuff is, let's call this this piece L, which is 2 pi R. Okay, so plus gamma LV times L, which is less than L0, plus B times curvature squared times, how big the object is, 2 pi R. Okay, and if you extremize, minimize delta U, that's to say the change between this and this, and the thing you get to change is, how much is wrapped up in a circle. You get L that goes with something like square root of B divided by gamma. All right? This object is called the Bandyopadhyay line. All right. So the idea is if the Bandyopadhyay, so this comes back to your question now of how thin should it be? Okay. You need to have LBC. If LBC is way, is tiny, then this thing will hold zip up completely. If LBC is bigger than the size of the object, it won't even close. Right? And LBC is controlled by the thickness. So this is maybe the first quantitative response to the question that you asked maybe half an hour ago. Okay. So what controls the system behavior is LBC divided by L0. Yeah? You take a tiny scrap of stuff, it will not fold on itself. Okay. You increase the length, it will. Okay. So the control parameter is size of system or the relevant length scale you have in your thing divided by LBC. And LBC is strongly controlled by bending modulus. Bending modulus is strongly controlled by thickness. T cubed for a sheet, T fourth for a rod. I'm going to show one more example now. By the way, why did I say all this Euler business? It's because this was what I showed you is a slightly, what did I do? I showed you this Euler business because we didn't get everything exactly correct. That's not the shape. That what I drew is not a tennis racket. It's, I don't know, table tennis. But it's, here are a bunch of, but if you do the exact Euler calculation, then this piece is a piece of an elastica. And to get the exact sort of boundary condition correct at the neck of the racket, you have to do a little bit of work. But in the end, the answer you get is that diameter that's marked over there, that's 0.89 times our LBC. So it's fairly close. I think this sets you up to solve, for example, a problem of two things that are flexible and you have capillary rise between them. You should ask, to flexible things, do you get bigger capillary rise? How much? Is it self-limiting? Is it just going to zip up? How far apart can you put things? It's also sort of a problem you can address of many brushes going into a fluid and coming out at the same time. Will they clump? How many will clump? I think this kind of calculation we did here is exactly what you need to do. Okay, I can spell out a few examples that you can try yourself on at home. Just wanted to say, everything we did was capillary driven. The gain here was all from capillary energy, but other kinds of addition can do it. So there's this nice paper that shows this in, collects examples. This is Cohen and Mahadevan, who find this is a single wall carbon nanotube. This is tubulin. Here's a simulation for a graphene sheet. And I thought I saw again in somebody's slides yesterday, something that looked exactly like a tennis racket. So anywhere where you have an addition that causes things to zip, but elasticity doesn't allow you to zip all the way, you get this kind of shape. Does this mean that I should stop? That's time for questions? Can I show you a movie before we start questions? Okay. So I wanted to show you, this is all planar 2D examples. I wanted to try and come back to the 3D world a little bit. And I wanted to show you this very elegant experiment by, again, the same set of people, Benoit Robin, José Bico. What they have here is a little bit of a plain version of the strip. And what they're going to do here is add a drop of fluid to it, just a drop of colored fluid. Okay. And they call it capillary origami. But you see the idea, it's in spirit like this. The fluid wants to grab the object, close it to reduce the liquid vapor surface area. It takes this thing and then they wait for it to evaporate and then it falls back again. Okay. So as the thing evaporates, there's less and less volume. So it starts doing this. When it's fully evaporated, it collapses. So what I want you to recognize is actually this thing is a very artfully done thing, both because these people know how to make experiments look very pretty, but also it's carefully chosen. So here's a whole bunch of other shapes that they did, you know, things that will close themselves, boxes, flowers, pyramids. But you see that they've made cuts in very strategic places so that things are always bending. Okay, you might think I'm trying to wrap a round object. This is not going to work by bending. But they've cut slits appropriately and tried to make that happen. So actually, in some ways, these are all 2D objects. If you take any cut of them, they're actually doing exactly what we've already talked about and learned how to estimate. You know, again, what happens here is the bending torque balances capillary forces, and you cut cleverly flaps. Again, you know, you can work through what the conditions for wrapping are. Here are two different videos. This square object, as it evaporates, you know, it tries to close in. And sometimes it just fails. Okay. There's the LBC and L0 need to be matched is the point. Okay. Can I get this guy to go? Okay. Yeah. This one tries wrapping, picks itself up by its corners, and then it suddenly decides it doesn't want that mode of wrapping. I'm not going to wrap by the corners. I'm going to wrap into a little tube. Okay. But essentially, so this is what the map over here is a diagram of LBC divided by L0, essentially, two different values of LBC divided by L0, and telling you the fate of something as you put a large amount of liquid and make it go to a small amount of liquid. This one never wraps, this one goes to a wrap state. Okay. It's really, and this is a schematic version of what they've done. You know, so it's still really 2D. This is another 2D experiment. This is from your next speaker. You see many examples of this kind of actuation in everyday life. So I'm going to stop there, actually. tomorrow we will really try hard to make things not go just by bending. We want to try and make it work harder. We want to try and see if we can't make that stretching thing happen. And we want to try and see if we're stuck, if the system always finds a way to do things purely by bending. Okay, we're going to make it harder and harder for the system to do so. All right. So question, sorry. I said movie and then I said that was movie plus 3 slides.